Hello everyone and welcome to our discussion on radiosondes. First we're going to look at the observation itself, the package that makes the observation. After that we're going to look at the analysis. So radiosondes, you probably know, are meteorological instrument packages that are carried aloft by a balloon. These are expendable, which means that they are lost once their job is done. They're very cheap, typically on the order of maybe about $50 to $75. Believe it or not, that is cheap for meteorological instrumentation. So typically they are lost afterwards, but if you do find one, you can mail it back. They measure the temperature profile, the moisture profile, in other words, the vertical profile of atmospheric variables throughout the atmosphere as it goes up, and it transmits that information down back to the ground. There's another term that we use, ray wind sondes instead of radiosondes, and a ray wind sonde is a radiosonde that measures wind. Now, we use these terms typically interchangeably. Old-timers tend to say radiosonde. People that in the know usually say ray wind sonde, but they are pretty much the same thing. Now, the instrument package that measures all of these variables doesn't weigh very much, only about 150 to 280 grams. A kilogram is about 2 pounds, so these weigh about a quarter of a pound or less. Basically, the weight of maybe 3 or 4 batteries. And there's a transmitter in there, very low power transmitter, 300 milliwatts, that sends information back down to the ground, all the information that's observed by the sensors. There's a number of sensors on this probe. It's got temperature, humidity, it's got a barometer that measures pressure, and then the wind is calculated by looking at the position of the radiosonde, and as it changes over time, they can determine the wind using GPS. It has a little GPS receiver and also a GPS antenna. So the balloon that carries this package aloft is a hydrogen-filled balloon. Typically at launch it's about 5 feet in diameter, but as it expands, as it gets to higher and higher levels in the atmosphere, that increases to about 25 feet, and it goes up very quickly, only about 1,000 feet per minute. The launch happens twice a day in select locations around the world. Typically our observations for radiosondes, we say it's a 12Z observation or a 0Z, but they start the launches at about 11 Zulu for the 12 Zulu observation and about 23 Zulu for the 0Z observation. And the reason for that is because it typically takes about 90 minutes to about 2 hours for the entire observation to be made. It takes quite a while to get up to 100,000 feet where the balloon bursts. And when the balloon bursts, the package comes down. It's got a parachute, and that slows its descent. But typically the packages will be found, the instrument packages will be found anywhere from 100 to 180 statute miles downwind of the launch site. And when weather conditions dictate, if there's severe weather, they will make multiple launches. In other words, they won't just do the 0Z and the 12Z. They might send up an 18 Zulu observation. There are 92 observation locations made by the National Weather Service. Those are in the continental United States, also Alaska, Hawaii, and all the other territories. But around the world, there's more than 1,300, and you can see that there's very good coverage over land, but not very good coverage over the oceans. So the information that we get from this, we get temperature and humidity and pressure, and we can plot that on a diagram, which is called a Skew-T log P diagram. The reason it's called Skew-T log P is because the temperature lines, instead of being straight up and down like you would normally expect on a Cartesian grid, they're skewed at a 45-degree angle. And then as you go up along the y-axis going up, or the z-axis, I guess, pressure changes logarithmically as you go up. So that is a log P, Skew-T log P. What we plot on this diagram is temperature versus pressure going up through the atmosphere, and then also the dew point. Now, typically temperature is red and dew point is green when we plot this, but there are a lot of places that don't plot color. So if it's black and white, then temperature is always to the right at warmer temperatures, and dew point is to the left at colder values. So what kind of analyses do we look for on this? Things that pilots can pick out are temperature inversions, clouds, the freezing level, and the tropopause. Temperature inversions are important. There are certain features that happen at temperature inversions that we'll talk about in other videos, but generally speaking, temperature inversion is where the temperature increases with height. And you can see here that it starts out at the surface, in this example, about 20 degrees Celsius, and it increases to about 25 by the time you get up to about 900 millibars. Typically, you'll see these temperature inversions early in the morning near the ground. Those are called radiation inversions, and they result from the ground cooling off at night, but the air above the ground, high above the ground, doesn't change too much in temperature. There are a lot of different other different types of inversions, and we will talk about those in other discussions. One thing that pilots can use the Skew-T log-P diagram for is identifying the bases and tops of clouds. So we can look at Skew-T log-P diagrams, and when the temperature and dew point lines get within 5 degrees Celsius of each other, we assume that there's a cloud. A lot of times they're closer together, but if they get within 5, then we start to think that perhaps there may be clouds there. Here's a good example of clouds at higher altitude. This is above 500 millibars, which is about 18,000 feet. And here's a very good example down low. In this case, we're looking at a cloud base of about 850 millibars. Remember that that is about 5,000 feet. And at about 800 millibars or 790 millibars, you have the cloud top, and that would probably be about 6,000 feet or so. So we know that the clouds are about 1,000 feet thick. Other things that you can find on the Skew-T log-P diagram is the height of the freezing level. The freezing level is where the temperature first reaches 0 degrees Celsius in the atmosphere. Looking at this, you can see that it is approximately 830 millibars on this diagram. You use the 0 degree isotherm to identify it where it goes through the temperature profile, and that represents about 5,200 feet MSL. Sometimes you have multiple freezing levels where the sounding goes through the 0 degree isotherm many times. This is extremely important for aviation, for pilots, because it'll tell you where the atmosphere is warmer than 0 or colder than 0. And when you have clouds, that can mean either icing or no icing. Another thing that's important for aviation is the tropopause, the height of the tropopause. The definition of the tropopause here, it's the lowest height at which the lapse rate decreases to 2 degrees Celsius per kilometer or less. I don't expect you to memorize that definition, but you should know how to look for the tropopause on a sounding. And typically at higher altitudes above 300 millibars, it's where the temperature stops decreasing with height, and from that point on stays the same or even increases with height. Remember, the tropopause is the top of the troposphere, and temperature decreases in the troposphere up to the tropopause, and then above the tropopause you have the stratosphere, where temperature is constant or increases with height. That's all we have for radiosonde observations and analysis. I hope you enjoyed it.